Hi everyone, I'm happy to present our project that studies the effect of count proximity in semi-weak label learning. This is a high-level outline of our presentation. Our project goal is to first analyze the impact of noisy semi-weak label data on model learning. Second, is to explore the effectiveness of using only pure deep learning method in such learning. So why are we interested in studying semi-weak label data? Because it is useful in real-world scenario, and only few researchers have studied the effectiveness of semi-weak label learning. It is useful because many times obtaining instant level label is not feasible or very expensive, and there is a great performance gap between strong and weak label learning. And also, during labeling process, noise is likely to occur in semi-weak label data sets because of human error. So the previous study that we are referring to as our baseline is the following. Our problem formulation, our project is a novel approach, as there are no published results that focus on studying labeling noise to semi-weak label learning. What we did is we replicate the model in previous study as baseline and introduced two types of noises to data set. In addition, we also modified the baseline model to better understand the effectiveness of only using deep learning approach to our experiment. And we have generated our three different data sets from CIFAR 10, and following is an example. So the design of our experiment is composed by two major parts. Part one is two types of noises introduced into our data sets. One is one-shot noise, which simulates the scenario of occasional labeling error made by the labeler. Second is unbiased noise, simulates the scenario of a malicious attack impacting large number of labels. So both, we thought of both noise to be interested in studying. And second is model modification. Instead of using the two-stage framework used by our baseline model, which includes an additional optimization step after deep learning model, we wanted to eliminate that piece because of the noise we added to bag level class. We want to eliminate the effect of such on instance level prediction. Second is we also want to study the effectiveness of only using pure deep learning approach in our semi-weak label learning. Below is the structure of our model. You can see that our input data is feeding in and formulates our semi-weak data sets, and then it is being fed into our deep learning from label classification, short as DLLC, and then during training it uses Poisson's law, and during inference we use argmat to get the instance label. And in terms of the DLLC, we use the ResNet 18, and you can tell that there is a optimization step being taken away from our model, which is the two-stage framework being used by the baseline. It's a post-processing done after deep learning model. After conducted all our experiment, we have gathered all our results together and provide the following analysis. So from table 4 on the right side, we can conclude three things. One is that noise negatively impacted our model performance. Second is that different noises has a different effect on our model performance. One-shot noise has a larger negative impact on performance than unbiased noise. And third is noise can boost the performance of weak learning tasks, especially when the bag size is large. And from table 5, the two-stage framework from baseline model only slightly boosted the instance precision. And we have two graphs here as well, and there is three conclusions drawn from these two graphs. Is first, adding noise does not significantly affect the rate of convergence. You can see from the slope of these curves. And second is a large bag size makes the model harder to learn, as it converge slower and also a lower precision. Third is that model achieves better precision when more training data are fed based on different data sets we have. We would like to conclude the following. We successfully replicate the model from our baseline paper, and therefore we can validate that semi-weak label can mitigate the gap between weak and strong label learning. Second is that the impact of noise on semi-weak label learning is that one-shot noise really affect the performance a lot more than the unbiased noise. Third is that pure deep learning approach is sufficiently effective with little performance drop compared to the two-stage framework that was proposed by our baseline model. Thank you, everyone, and for more detail, please refer to our paper. Have a nice day.